Hello and welcome to our fifth and final video on our series of vapor-liquid equilibrium. And in this video we're going to be talking about the lever rule and using it to explain how the ratio of the vapor to liquid fractions will change in a closed container if we have a fixed temperature, so knowing our temperature, but we have a continual increase in pressure. What is going to happen between the liquid and vapor phases and the compositions of those as the pressure continues to increase, and then as the concentration transition from all vapor to all liquid. So we're going to dive into that here. Let's go ahead and make this full screen here. So with the lever rule, we have a graph here where we have our x and our pressure. Our temperature is known. We could even say it's at 393 Kelvin. It doesn't really matter. Just the concept is that we have a fixed temperature, and we have our graphs here. And so, actually, let me make these two different colors, because this will signify this is our dew pressure curve, and this is our bubble pressure curve, because this is our, this is all liquid up here, and this is all vapor, because again, as the pressure increases, then it's going to condense into the liquid phase for whatever our content mixture is. And let's say that our feed right here is our Z1. So this is our feed coming in. Go ahead and call this the feed. Now at the feed, actually that's that's fine. For that feed, we're going to see that we have our composition is going to be the Y1. It's going to be a certain amount of the composition is going to be in the vapor phase, and then a certain amount of the composition is going to be in the liquid phase at that particular pressure right here for the feed. When the feed is at this temperature, whatever the temperature is that's known, and this pressure right here, then it's going to be an equilibrium between this much of our composition in the vapor phase and this much in the liquid phase. Now the reason we call it a lever rule is because it's going to operate like a seesaw. And so if you have a bunch of the weight here, then that means this is going to be elevated. And so the closer this is to the ground, the further this is going to be off the ground. And then vice versa. If we then shift and then push it the other direction, and this is really close to the ground, then this has to be off the ground. So, and then if they happen to be in a close, or they were in equilibrium, well, they're in equilibrium all regardless here, but if they were completely like equalized out half and half, right, then they're going to just be an equal ratio with that. So the concept is that as one increases, the other decreases, and so they're gonna be operating like this with each other. So that's the concept of this seesaw, this lever rule. So let's go ahead and use our mass balance equations to walk through this and to see how these vapor and liquid compositions are going to change in their ratio formats to each other. So for our mass balance, let's make sure it's showing up there. Good. We have our feed equals our moles, our number of moles. This is also our number of moles total. This is our number of moles in the liquid phase plus our number of moles in the vapor phase. And then, so if we put in our composition balance, then we're going to have whatever the mole amount in the liquid phase multiplied by the composition of that, the mole fractions in the liquid phase, and then same thing for the vapor phase here. So then let's go ahead and start to unpack this a little bit so that we can set the vapor and the liquid as a ratio of each other. So we're going to go ahead and do that now. So F, let's go ahead and not write F. Let's hit erase there. We're going to substitute this in so we can get rid of F. And then let's go and let's bring let's factor the Z out, because then what we're going to do is set the vapor to one side and the liquid contents to one side, which leads us to being able to say that once we bring this over and this over, we'll be able to say, let's see, pull out the liquid minus x1 equals, bring out the V for moles in the vapor phase. It's going to be y1 minus z1. So this is setting the phases to each side, because now we can set our equation to say, bring it right here, that our vapor to liquid ratio is going to be z1 minus x1, y1 minus z1. Now what the significance of this is if we come back to here, we got our x1, our y1, our z1. Again, we're going to draw our temperature is known, and we've got our bubble pressure. What colors did I do? Blue on top. So our bubble pressure curve, and then our dew pressure curve. And if we, let's say we say our feed is right here, this right here is going to be our mole fraction in the vapor phase, which is going to be in equilibrium to this over here, which is going to be our mole fraction in the liquid phase. The thing we can say is that the distance between this, so Z1 minus X1, which is what we have right here, and the distance for Y1 minus Z1, which is what we have in the denominator right here, that ratio is the ratio between the vapor and the liquid mole amount. So this is the lever rule. We have our feed, Z1, whatever Z1 happens to be along this point. For it could, I mean, it could be down here depending on the pressure. It could be all the way up here if the pressure continues to increase. But wherever our Z1 currently is at for our known temperature and whatever the pressure point is currently at this point it's here, whatever the ratio between Z1 minus X1 to Y1 minus Z1, that distance ratio, so if this were to continue to come up here, this distance would decrease and this distance would increase right there. And so that ratio between the Z1 minus X1, that distance to the Y1 minus Z1 distance, the ratio there between those two things is the ratio of vapor to liquid that we would obtain. And as we can see, this is operating as our seesaw would, because as this increases, this must decrease. As this goes further from the ground, this must come closer to the ground. As this side goes further from the ground, this side must come closer to the ground. So they're always moving like that, which is the same thing we see happening here as this as the pressure continues to increase closer and closer to becoming all liquid. We have all liquid up here and all vapor down here. Then as this continues to increase, the fraction between the liquid to as this continues to increase to more and more liquid, then the fraction of the difference between vapor to liquid decreases. And and then as we continue to come down here, we're coming to all vapor. And let's go ahead and draw that out down here. So we have our pressure. Again, we have our XY, X1 and Y1. We have our bubble pressure. We have our dew pressure. And let's say our Z1 starts right here. Well, right now, we are 100% vapor at this point. This is 100% vapor. But as the pressure continues to increase, we finally hit this spot right here. This is our Z1. But our Z1, at the moment we hit our Z1, that is the dew pressure, right? Which is when at a known temperature we've asked at what pressure does the first drop form from our mixture, which is 100% vapor. When does the pressure continue to increase so that our first drop forms in the vapor? And whatever that first drop is, when that happens, it's going to be this right here. This is what our liquid composition is going to be, because the X1 and the Y1, which is currently the Y1 currently equals Z1 there. These are in equilibrium to each other. The moment we continue to increase our pressure though, and we have it right there for our Z1, now we're in between the bubble pressure and the dew pressure curves. And in the last video we saw that this is part of the concept of separation, and separation happens when we're in between these curves, because now we're going to have some that is going to be in the vapor phase and some that is going to be in the liquid phase. And so now we have again our ratio of whatever is in the vapor phase to whatever is in the liquid phase. That is the ratio between the distance from our liquid composition to our feed to the ratio of our feed to our vapor composition. So that is going to be the same ratio of our vapor to our liquid phases and mole amounts. And as we continue to increase all the way up, now we finally hit the bubble pressure curve, and this right here is our X1, meaning that we've hit 100% of our mixture now. 100% of our mixture is in the liquid phase. With the increased pressure, as the pressure has increased, we now have condensed all of our mixture that was vapor, and it's now completely become all liquid, because right here would be our Y1. And so if we were coming the other way, and if we were starting at 100% liquid and we started to decrease the pressure at our known temperature from here, let's say our Z1 started up here and we worked our way down, well, now we've hit the point where we've said at a known temperature, at what pressure will the first bubble form? And when the first bubble forms, the composition of that bubble, the vapor composition of that bubble, is going to be right here at our Y1. And so this is why it's called the lever rule, because it's operating as the seesaw. We start with our feed, 100% vapor, continues to increase the pressure. We hit this right here, our dew pressure curve at this point, and when that first drop forms, the composition of that drop is this right here. This is our liquid composition of the drop. We continue to increase. Now we have separation. We have two states of our mixture. Some of our mixture is going to be in the vapor phase, and some of it is going to be in the liquid phase, and the amount is going to be, this is going to be the composition of our vapor phase and the composition of our liquid phase, and then the amount that's going to be in the vapor mole amount versus the liquid mole amount is the ratio of our distances between our x1 here, and our z1, and our z1, and our y1. So that ratio is going to be the same ratio of what's going to be in the vapor as opposed to what's going to be in the liquid as shown by this. And so this is the lever rule in action, and then going back to what we wanted to be able to show, which is the contents transition from all vapor to all liquid, which is what we've done here. We started with all vapor, continue to increase the pressure. We've seen what's happened, and now appears when it transitions to all liquid. And if we were coming from all liquid down to here, and we formed our first bubble, this would be the composition of that bubble. Thank you for being part of this video series on vapor-liquid equilibrium. Have a good day.